You know that for any function f, each x value in the domain corresponds to exactly one y value in the range. For a one-to-one function, it is also true that each y value in the range corresponds to exactly one x value in the domain. A one-to-one function f has an inverse f inverse that is also a function. If f maps a to b, then f inverse must map b to a. Consider this diagram. On the left, the domain of f and a particular input value a. The function f applies a function rule f to the input a and leads us to the range of f and some output value b. Note that f and f inverse are both functions. So b now becomes a domain value of f inverse, so an input into the inverse function, f inverse. The function rule of f inverse gets applied to that input b and maps it back to a in the range of f inverse. That brings us back to where we began with a. And here we can see that a can be considered in the domain of f, but also in the range of f inverse. We can also consider a is mapped to b in the function f, and b is mapped to a in the function f inverse. Take note, key concept, composition of inverse functions. If f and f inverse are inverse functions, then f inverse of f of x equals x. And f of f inverse of x equals x, for x in the domains of f and f inverse respectively. This says that the composition of a function and its inverse is essentially the identity function. The identity function of x equals x, or y equals x. Problem 6. Composing inverse functions. For f of x equals 1 over x minus 1, what is each of the following? Part A, f inverse of x. Well, we'll rewrite the function in function notation. F of x equals 1 over x minus 1. Then we'll replace the function notation, f of x, with y, and have the equation y equals 1 over x minus 1. Now we'll switch x and y in order to begin to create the inverse function, and isolate y. Note y for the time being is kind of stuck in the denominator of the fraction on the right. So what we'll do is multiply each side of the equation by the entire denominator, y minus 1. So on the left we have x times the quantity, y minus 1, and on the right, 1. Then we'll divide each side by x as we work to isolate y. This brings us to y minus 1 equals 1 over x. And finally, add 1 to each side. Y is isolated in the equation y equals 1 over x plus 1. We'll replace y with function notation and the function inverse and state. So, f inverse of x equals 1 over x plus 1. Part B. What is f of f inverse of 1? Well, rewriting f of f inverse of 1 is the same as f of f inverse of 1. F inverse of 1, well, that's 1 over 1, our input value, plus 1, and that's 2. So now we find ourselves evaluating f of 2. F of 2 is 1 over 2, our input value, minus 1, and that's simply 1. So f of f inverse of 1 is 1. Part C. How about f inverse of f of 1? Well, as we begin, f inverse of f of 1 is the same as f inverse of f of 1. F of 1 is 1 over our input 1 minus 1, and that's 1 over 0, which is undefined. So f inverse of 1 over 0 is undefined, and we can state, or point out, 1 is not in the domain of f. Therefore, f inverse of f of 1 does not exist. Your turn, part A. Let g of x equal 4 over x plus 2. What is g inverse of x? Part B. Let g of x equal 4 over x plus 2 and g inverse of x equal 4 minus 2x over x. What is g of g inverse of 0? Part C. Let g of x equal 4 over x plus 2 and g inverse of x equal 4 minus 2x over x. What is g inverse of g of 0?